All right. Okay, so let me just adjust this here. Cool. All right. So good morning, everyone. Happy whatever day today is, Thursday. So today we're going to do our, like not the official class time, but this will definitely be put on Panopto. Always encouraged to just show up to these because it's better to show up and be able to ask questions live, as opposed to like, what was he talking about, and then have to, ask over email, which is a little bit more difficult here. But what we're going to talk about today, I'll kind of wrap up what we were talking about at the end of class on Wednesday last time. And that differential equation I had you guys solve. Then I have a few announcements, and then we'll look at stable solutions to differential equations. And go back to section 1.1 and talk about slope fields and what's a slope field. I'll talk about that. And also section 1.3. So yeah, this will be 2 hours. We'll do kind of like a 1 hour chunk. I'm going to hit pause and then, give us 5 minutes or whatever, walk, take some time away from the screen for a minute. I'm taking time away from this camera for a minute, and then come back rejuvenated for something new here. Okay, so I do want to look at the differential equation we solved before and talk about it in context a little bit too. Let's just look at this differential equation though. Find the general solution to dy by dt equals y, right? Oh, and notice, I don't know if you all notice anything different about this whiteboard? Notice that it's not angled away from you anymore. See how it's like nice and flat? And same with this one, right? This one was worse, right? Look at this. There's this, I'll draw a square here, right? And see how it's a square, you can see it. Whereas before, it was like way back here, it was like back here. Now I can like hide, from you guys. I can hide from you. I don't know if you could hear me when I was back there, but improvement, right? You'll see some more improvements. I got to figure out how to improve the video quality. I feel like I can do that. And the sound. I have some methods for improving the sound quality. I think you all can kind of hear me though, right? Like, but anyways, just thought I'd show that out to you. Cool new angles to the whiteboard. You can kind of see there's like a weird angle here. I don't know if you can tell. There's like a V shape right there. All right, so going back to our problem at hand here, find the general solution to this differential equation, dy dt equals y. So let's just quickly run through what we did yesterday, but I want to talk about, I'll add the absolute value thing in a second. I won't do it right away. So we do separation of variables, 1 over y, dy equals dt. And the way we got that, I'll just put it here. We divided by y, right? And we multiplied by dt, right? Which is kind of naughty, but whatever, right? We canceled, and that's what we end up with. Then we integrate both sides. Integral of both sides. And we know that this is natural log of absolute value of y equals t plus c, right? And we kind of mentioned yesterday when we do this, you can always do a C1 and a C2, but when you do the separation of variables thing, just do a C on one side. It does not matter which side, because we kind of talked, there's that constant algebra thing. And when we solve this for y, because I said explicit solutions are kind of the best, we get this. And then I'm going to put like a big frowny face, because I want to come back to this step in the next thing that we talk about. We'll talk about this problem for a bit. I'm just dropping the absolute value for now. Cool. So we end up with this solution. Here's the algebraic steps, right, to get our general solution. And we talked about this, right? Yeah, this is the general solution. You know, different values of c, e to the 5, e to the t is a solution, 6, e to the t is a solution. Those would all be initial value problems depending on the initial conditions. So let's try an initial value problem. And it'll be pretty straightforward. And when we're done, let's do 2 initial value problems. And then when we're done, I'm going to come back to this absolute value thing. I think it's easier to see once we do these 2 initial value problems why I'm okay just dropping the absolute value here, right? It kind of like makes more sense once we do that step. You know, it's like do this thing, then come back to this weirdo thing. Okay, so I said 2 initial value problems. Solve the IVPs. So I'll do A, y of 0 equals 7. And let's do this one, B, y of 0 equals negative 12. Right? So, all right, to do this, we get our general solution. I'll just put it right here. Right? There is our general solution. And we plug in t equals 0, y equals 7, likewise here. T equals 0, y equals negative 12 for these 2 different problems. I like writing it like this. I've mentioned that because I easily get things mixed up if I don't, right, what the y and t are. So, okay, so I plug those in, and it's pretty straightforward here. 7 equals c e to the 0. E to the 0 is 1, so c equals 7. And we end up with y equals 7 e to the t. And that's our solution to the initial value problem. And now we do this one. It's like pretty similar. But the reason I'm doing both of these, you will see, why I kind of was able to skip that absolute value thing. Okay, so here we go. Y equals negative 12 e to the t, right? Okay, and that's my, initial value problem solution to this guy. Okay, now let's go back to this absolute value thing. Why I skipped it. It's kind of easier to see once we've done those 2 problems. I'll do this correctly without skipping it to remind ourselves how to, I'll turn this brown upside down. And let's go here and correct this. I think it's just easier to see after we do those 2 problems. To do this correctly, to solve this, I need a plus or minus. This is how you solve an absolute value equation. Right? Is that fair? Because this could be positive or negative, right? Just kind of, very much like x equals absolute value. Oh, wait. Quick algebra review. Get this correctly. Right? Kind of makes sense. If this is your equation, absolute value of x equals 5, the 2 solutions are 5 or negative 5, right? Because if you plug negative 5 here, you get 5. If you plug 5 here, you get 5. Same thing, but it's just more complicated because it's y's, e's, and all that stuff, right? But that's how you solve an absolute value equation, right? drop the absolute value, add a plus or minus. And now let's do those steps before. Y equals plus or minus e to the c, e to the t. Now, take a look here. This kind of comes back to that weird constant algebra that we talked about. Notice I could leave that plus or minus here, and it just changes what the c is when we get to the initial value problem, right? If you have a positive right here, you end up with c equals 7. If you have a negative here, you end up with negative 12. And that plus or minus kind of just gets absorbed into the constant, the same way that that e to the c is just a different constant, right? You know, like it's kind of like, okay, c has to be technically, is that fair? One thing to notice, e to the c can never be negative, right? This is always a positive number. And but this can be a negative number, right? So you could kind of be like, okay, the plus or minus can technically be dropped here by saying c is either positive or negative, kind of getting rid of that domain restriction on c. Because technically, you know, this is always positive, but c as a variable can be positive or negative. So you kind of like combine this into a c that can be positive or negative. So anyways, it's pretty subtle. Don't expect me to put a test question on something like that. But we end up solving this differential equation a lot this quarter. We're going to use it a bunch. And at some point, I'm just going to, whenever it says dy dt equals y, I'm just going to jump to this guy right here. So you should kind of be familiar with this one and know that that c can be positive or negative, depending on the initial condition, right? Okay. Now let's talk about this in context, right? Let's go back over here. I think I did y last time, yeah. I'm going to change it a little bit.
Hey, Professor.
Oh, what's up? Yeah, hey.
Hey, so I'm trying to understand that the notation of the absolute value. So when we do have an absolute value notationally, we can drop it on account of that c having the power to be either positive or negative.
Mm-hmm.
So does that mean that anytime we see an absolute value, it wasn't kosher yesterday, but it's kosher now to just drop it and assume that?
Yeah, I think because like I kind of like what I'm kind of doing here is just walking through how I can drop that absolute value this one time, you know, and then in the future when we see this, instead of doing every step and like being rigorous each time, I'm just going to jump right to that c e to the t, right? You know, now this is a good explanation why we're, you know, like, because what I don't want to do is be like, oh, like brush it under the carpet and forget about it, you know, because you should know that this is, you know, I don't want to instill that habit. Some people will just forget about that absolute value, right? And just brush that under the carpet. But I want you to remember that this antiderivative is ln absolute value y, but just the nature of how we're solving this differential equation, that absolute value could have been ignored and you end up with the right thing, right? But this one time, I want to show you why you could ignore it and you end up with the right answer, you know? And in the future, we will just ignore it. I'm just going to go boom to that last thing because, you know, if we do this, we're going to end up solving, this will end up showing up several times throughout the quarter. What I don't want to do is each time do 10 minutes of each individual step, you know, because we're focusing on some other thing. And then like, oh, this absolute value thing, what are you talking about? It's just like, you know, too much, right? So keep this in your notes. Maybe at some point you want to refresh and remember that. That's great. But when we're talking about, systems of differential equations and we have these other concepts, I don't want to like have to get distracted with this other chore here. Cool.
Thank you.
Yep. And was that Skylar that was talking?
Yes, that was me.
Cool. Yeah, I want to try to ask names so that that way you all know who each other are too. Try to make it real. Okay. Let's look at one other thing. I'm going to change up this differential equation a little bit and solve a similar one. Find the general solution to dp dt equals some constant k times p. Okay, so very similar. I'll just run through the algebra pretty fast. It's the same thing, but p's and there's an extra k. I'll skip some steps. And then kind of talk about this one a little bit more. All right, so we've seen this is familiar. Antiderivative, ln of absolute value of p equals k t plus c. And then what we're going to do is remember, now I'll put a smiley face. Just drop the absolute value, because we kind of saw why that was okay. And say p equals some e to the k t plus c. P equals c e to the k t, right? Now, let's take a look at what's happening here. Okay, so solved it, nothing new, right? You just ended up with a k. The k here puts the k here. That's the algebra here. But this differential equation is pretty important, right? Now, it's important because we often use this as a simple population model. A simple population. That's why I use P. I'll put a box here. And this is kind of putting context to these differential equations. The reason why this is a good, simple population model is what this is saying. Let's turn this from an equation to words. Thinking about what does this mean in terms of words? The rate of change of the population is proportional to or equal to, with a constant, the current population, right? What happens to the rabbit population in the park if you double the number of rabbits? If you double the number of rabbits, there's twice as much biology happening, the biology of rabbit reproduction. Twice as many litters of baby bunnies are being thrown, and the rate of growth is going to be double. If you go out and you are a fox and you eat half the rabbits, what's going to happen? You eat half the dads, you eat half the moms, and you have half as many litters being thrown, right? And that kind of makes sense, right? Increase the population and you have larger growth, decrease the population and you have lower growth. And this is also why populations grow exponentially, right? You've probably seen that, like the human population has been kind of growing exponentially for some time now, right? So yeah, this kind of behavior leads to this kind of a result here. Now,
Question.
I said, is there a question?
Yeah. So in that model,
talking to, I always like to ask.
Can you hear me? Yeah.
Yeah. Oh, who is it talking?
Raul.
Oh, okay. Hi, Raul. You have a question?
Yes. So in that model, the K, is that a parameter?
Yes, yes. This K here, so P is the population, right? Let's kind of put this here. Simple population where P is the population, obviously. T is, and you could have units, whatever you want, individuals, millions. T is time gone by, right? Whatever units, it doesn't matter. And then K is a parameter or constant. And in this, since we're talking about it, right, I didn't want to mention this, but in this context, K is going to depend on the, the reproductive rate of the population, right? So for example, something like bacteria is going to have a very large K. Right? Bacteria is going to have a large K because is that their bacteria, bacteria maybe like on a hot dog you leave out on a plate, because the bacteria is going to double, like every, hour or something like that, right? The bacteria, they split pretty quick. Or something like an elephant, which have like gestation periods of like 16 months. Oh my goodness. Or like blue whales, I don't know what their gestation period is, like 2 years. K is small, right? So kind of depending on what the animal is or whatever the thing, doesn't have to be an animal, it could be a bacteria or plant, will determine what that K is, right? And that makes sense, bacteria, double pretty quick. Elephants, they'll still grow exponentially, but not quite as quickly here. Okay, so let's see. We talked about all this. Now, I also put here, I do want to mention this. I'll circle some words here. It's a simple population model. Now, what I did not write here was the population model because there's flaws to this population model, right? It might be accurate on some domain, but, oh wait, let me plug in my laptop. I just noticed it came unplugged. And I don't want the battery to come out. Okay, cool. All right, it's accurate on some domain, right? Those bacteria are gonna double and double and double, but are the bacteria gonna double forever? Eventually they're gonna run out of hot dog to eat. The resources will run out. The elephants, humans too, right? Our population is growing exponentially, but we're on this earth, and kind of like in our lifetimes, maybe we'll see that population stop exponentially growing, unless we come up with some sort of like more land mass for us to move on to, some other resources we can devour, but we're going to run out of resources. So it's a simple population model because human population, maybe we can get to 20 billion people, maybe we can get to 40 billion people. That sounds insane, but I don't think we can have a trillion, 1,000 billion people. That's like, or a trillion, right? Because this would let you get to a trillion people. There's just, at some point, we're just going to be like stuck like sardines to each other, it's just not going to be possible. So it's a simple population model. And later, we'll look at some other population models that account for the fact that this, there's going to be like some point where you just can't grow anymore. Or maybe some other population models will look where there's a predator, right? As there's more predators, your population goes down, and we can create all sorts of population models that, reflect those things. As predators increase, rate of population goes down. As predators decrease, maybe we have more population growth, right? Whatever you want, add another variable and make it account for this change here. And it's also a population model. Someone could come up here and say, you know what? I think this should be related to the third power or something like that. Go ahead, solve it. I don't know what it'll look like. Probably not be an exponential. And maybe that's more accurate, right? Maybe for some form of fungus, you know, for whatever reason, maybe the fungi, just the way they behave, it looks more like this. Because remember that these models are made for us to look at what's happening, what we see. The elephants, the bacteria, and the fungi are just doing their thing. They're not looking at this differential equation. They're just doing their fungus thing and reproducing themselves. We create these as just like, kind of like words in some way to describe what we see. And those words have limitations to them, right? And sometimes one word might be better than another. And if this isn't working, it might be, it's not that there's anything wrong with the model, it's just not a great model to talk about those things. So limitations, right? You know, it's not like those populations follow this. We just use this to like, okay, we see them doubling, how long until they get to 1 billion bacteria? And maybe it's accurate, maybe not, but it gives us something to think about, following the trend, assuming the trend continues. Okay, okay, I think that's the spiel on that. Let's take a look at two things. One, I want to put an advertisement out for, I'm going to go to share screen here real quick. Oh yeah, I have a video to play for us. Oh, someone said carrying capacity, that's right. And we'll look at that model. Who said that? Oh, Aaron said that, like a carrying capacity. That's right. We'll look at a model that kind of accounts for carrying capacity, where maybe, you know, it's like the population becomes flat at some point. You know, there's just enough resources to keep the population going. And then we'll see what's called, and we'll look at it in a second, a stable solution, right? Where the population can't go higher and can't go lower. Or if it does go higher, the stable solution kind of like has pressure to go back to that stable thing. If it goes lower, the rabbits are like, cool, there's more food we can devour, and they rise back up. Cool. Okay, so two things I want to put on the share here. Oh yeah, there's this. Under discussions, I put a couple things. I'll move this till Monday, I think. I did put a beginning of the quarter introductions, so it's an assignment on Canvas. So check it out. It's just like, hello, who are you? You know, you can meet each other virtually, blah, blah, blah. Looks like some people did some stuff. You can chat with each other. I think, yeah, see if you have common interests, whatever. So do that. Also, there's this guy, NCAS. That's, oh, let me do this. Hello. Okay, NCAS, that stands for National Community College Aerospace Scholars, right? So they're accepting applications in now. And what this is if you are a community college student, which I think you all are, right? You apply for this, and it's kind of like you take, it's normally even non-COVID times, you get enrolled in an online course, kind of like this, and you have some discussions, and there's people all over the country, and it's pretty cool online class. It's all about space and like, what does sound like on Mars? And they have all these cool questions. People who do it tend to think it's pretty cool. They're just interesting, fun projects. Not too time consuming. Like, I think what I've heard is like maybe 5 hours a week. And if you do well, then you can be admitted to go to, you see here, free trip to space camp, right? And I'm advertising it because at Central, over the past several years, there have been several people who've gone to this space camp. It's not like a lottery where, yes, you theoretically could go to space camp, but out of the 100,000 people, only 2 do. But if people from Central seem to go like 2 or 3 people a year, then I think it's worth advertising, you know, because that could be 2 or 3 people in this room who go, you know. So there's these sessions. Obviously, this one's passed. You can click them. I think it just goes to some links. Here's a flyer about it. And I did want to play, here's a video advertising it. So I'll go do this. Yeah, I'll just play it, right? Since you're all here. I'll hit play.
Courage. Being smart is given, but it's your determination, it's your passion,
Oh, wait.
and it's your creativity which binds you together and makes you suitable for next step.
Can you hear it?
Is that something they asked you guys to do? It makes sense.
Even when applying, I felt kind of nervous because NASA seems like this huge entity that's like untouchable and almost like scary. But when I came here, I noticed that a lot of the employees were easy to talk to, and they just wanted to engage the minds of future engineers and scientists.
We're basically had to put ourselves into these roles that were very much similar to what NASA does for their projects. We had a game plan of what kind of rover we wanted to build, and then we had an assembly team build.
Okay, I heard that the video is not sharing too well, so you know, not the best environment for it. So what I'm going to do is just put the link in the chat, right? So watch it on your own, and I'll try to send that in a Canvas message later too. But definitely check it out. And I think it is, someone also asked, I think it's only eligible for US citizens to go to space camp, but I think that anyone might be able to do the online course thing. I'm not 100% sure, but pretty cool, right? I would definitely check it out. So let's see. Next on the
It's just U.S. citizens. I think I was able to do it, and I have dual citizenship. So.
Oh, okay. Cool. And you like? Oh, yeah. You did it in the fall, right? Is this Cat?
Yep.
Cool. And was it cool?
It was cool. It was fun.
Yeah. Yeah. So check it out. You know, and it's free and it's cool. Even if you don't go to space camp, it's cool. But maybe people do. I think it's like people do. Okay, let's see, what is next? Where's my piece of paper here? Okay, what I was gonna do next is give you all a differential equation and then throw you in the breakout room for just a minute. If you're watching this on Panopto, just push pause and call your friend or something and Zoom with them. I don't know. Okay, so using, I gotta change my camera here. I was like, this is not working. Okay, we're back. So weird. Okay, so find the general solution using separation of variables to this differential equation. Now there's kind of a trick to it. I haven't covered it, but what I want you to do is look at it for a minute and then we'll compare. So I'm going to throw you all in the breakout rooms. I'm going to push pause on the record. Okay, so hopefully what you all did, I jumped in a couple breakout rooms, but the best method here, and in general, when using separation of variables, the key is always factoring, right? If you can factor, then you can solve it by separation of variables, right? So you end up with x to the negative 2 dx equals 2t plus 3 dt. We integrate both sides. Oh, geez. That becomes, I think, negative 1 over x equals t squared, oops, plus 3t plus c. And doing some algebra, I'll kind of skip some of the algebra, just jump to it. But you should have ended up with something kind of like that, right? Negative 1 over t squared plus 3t plus c, right? But the two rooms I jumped in, people seem like pretty good with that. So,
I have a question.
yeah, who is it?
Raul.
Okay, hey Raul.
Hey. So to test that this is a solution, then we would have to differentiate it, right?
That's right. I'm not going to do that. But to test, right? I mean, just because class time, right? Take the derivative, right? And that derivative
Should be equal to the 2tx squared plus 3x squared.
yeah, this you would plug in right here, but then you also got to plug this twice, right? Or I guess you could, right? You just plug it into here once. That's a little easier, right? And just square. I just don't want to do this in class, but squaring that and then differentiating and it should all work out though, right? You'll see.
Okay.
Same on both sides. You probably have to FOIL or something. I don't know, but you can kind of tell, right? If you do quotient rule, is that fair? You're going to have this squared in the denominator if you do the quotient rule, and this x is squared from that. I think that's kind of where you can. I'm like doing it in my head a little bit, right? You know, because x squared puts this in the denominator. That's kind of my quick check. But do it for real if you want, and it should work out.
Okay, thanks.
Cool. Okay, so what I want to do next is, maybe we'll just zip over here, is going back and forth a little bit. We did not finish 1.1, but what I want to do is, so we have the whole 2 hours, right, which is cool, talk a little bit about slope fields, which I think is 1.3, and then come back to 1.1 with some more stuff about the population model. I just think it's a little better if we cover 1.3 first. It'll make a little more sense. So take advantage of these 2-hour sessions here. So this is a visual understanding of, it's like a visual way of solving the differential equations, right? What we did over here was algebraic, right? But now we're going to have like a visual way of solving it, and it'll lead us into another method we'll see next week probably. Okay, so slope fields. This is 1.3, and then we'll come back to populations again. Slope fields 1.3. Oh, am I recording? Yeah. Oh, and I want to start Mathematica because it's slow. Okay. Okay, so the slope field method only works really for initial value problems. Let me fix this. Okay. So solve the initial value problem graphically. All right, so I'm going to put the differential equation over here. Ta-da. Okay, so here's our deal, right? The question is kind of right here. Here's the differential equation. Here's our initial value. And I just wrote it in a different way right here because I like that better. And we're going to solve it visually. Now, I'll do this by pen and paper or whiteboard and marker in class now, and I might do it a couple times, just real quick. But for the most part, this method is something where we are going to use Mathematica. Now, I'll do Mathematica in a minute, but I think it's best to kind of show by hand how to do it, you know, so you get an idea of how this works. And then we'll look at Mathematica and be like, okay, Mathematica is just better at doing this. It's one of those things like it's tedious to do by hand, right? So to do a good job, we ask Mathematica. But for that first time, right, you know, it's like you gotta do it once by hand to see, so that way you're not just like, this is what Mathematica just told me. So you make a big Y versus T graph right here. And then what we're gonna do, put this pen down, put this down too. We're gonna kind of make like a little grid. I mean, this technically is a grid, right? Different values of Y and T. And what we're gonna do is plug those values of Y and T here and draw a little line that represents the slope here. So for example, let's just do this basic one. T equals 0, Y equals 0. 0 minus 2, 0 is 0. And so what I'm going to do is, since it's 0, I'm going to put a horizontal line there because that has a slope of 0. Then what happens when we go to T equals 1, which is right here? Plug in T equals 1, Y equals 0, and this is equal to 1. So I draw something with a slope of 1. You can start to see how Mathematica is probably better at this than me, right? T equals 2. That's my best attempt at drawing a line of slope 2. T equals 3 and 4, right? And now what happens if I do T equals -1? -2, -3, and -4. Okay, and then what we do is we fill this in with all the different values of T and Y. And we're like, oh my gosh. So now we're at, we'll do one more row, then I'll kind of speed things up. Y equals 1, T equals 0. I get -2. Then -1. Then 0. Then 1. Then 2. And I'm just going to say these get steeper, right? Okay, then we kind of go through, if we went through this even further, we get a super steep thing, less steep, -1, and 0, right? And then it's like, okay. We could continue to fill out the board, right? But what I want to note, this is kind of a trick for slope fields. A way to help understand it is asking the question, and this happens when we do Mathematica too, right? When is this equal to 0? Y equals 1/2 T. Everywhere along here, see how there's a 0 here, a 0 here? There's going to be a 0 here. Notice that -1 for Y and -2 for T. Right? So everywhere along here it's 0. And what you might notice is the slope is always like negative when we're above. This is more like right here. Oh wait, no, this was more like right here. Right, and so negative. And then always positive when, I'm just like drawing a bunch of lines, you know, but that's what this is. Now you can see that this is like, you know, pretty sloppy here. Okay, now what I want to do is go to Mathematica. I'll open it up and we'll look at a much better slope field, right? This is kind of how you do it by hand. You can kind of see the two things that are important. You can either just plot these by points doing the individual values, but it's also nice to like notice where 0 is, right? 0 is along the line 1/2 t. For different things, it's somewhere else. Okay, let's open up Mathematica. I'll share screen. Did I open a new notebook? And you're going to, what I'm going to do is use something that has the Seattle Central package here. So hopefully you downloaded that. Oh, actually, I need the newer version. I have 2.4, whatever, no big deal. And there's two versions of slope field. There's slope field. Okay, here's also my Mathematica trick. I always hit those double arrows down. And my computer's sometimes glitchy. Come on. Right? Because it tells me the code so I don't mess up and do 2 commas instead of 1, right? So now I just fill in the blank. And what this is saying is, what's my function of x and y? Ours is not x and y, it's t and y, right? Which is fine. But our equation is 2t minus y. Is that what it is? No, I lied. It's y minus 2t, right? Copying. No. I'm like super dyslexic here. T minus 2y. There we go. There. So we do our equation here, and then it just wants to know what our values that we make the thing with. So I'm going to do t. That's t not x. From how about -5 to 5. And let's do y from -5 to 5. Cool. And you can see this kind of looks like my slope field. Now, they kind of like did a little grid where they didn't land exactly on, you know, they didn't end up with those horizontal lines because how these are spaced. There are horizontal lines. They're just like probably right along where my mouse is. And let's hit the chat. Okay. Okay. No worries. But yeah, check this out if you have to bail out on the Panopto. Panopto is still giving me issues with uploading. It's like just super slow. Like today it was better, but I had to stop it because of this. I can't have it uploading while I'm doing this. But I think things will get, yesterday's thing will get uploaded today. It's just going to take 3 hours, and this will probably take 6 hours to upload. So just leave my laptop going for however long. All right, so there's slope field, right? It draws it. Now remember, I said we drew a slope field, but we want to find visually the solution to this differential, this initial value problem. So what you could do, I'll do it on this thing. You could just kind of follow the trajectory of these lines, right? You could kind of just be like, oh, hey, look. You know, if I go back to, if I stop share and I go to mine, I'll just leave it like this, right? You just kind of follow these lines. You know, it'll do something kind of roughly like that. But, you know, doing it by hand with my slope field is pretty lame. So let's do it on Mathematica. And we'll see it's about the same, you know, it's better though. This doesn't allow that option, but there's another command here, DE solver. And I always do the double chevrons down. No, come on. And same thing, you put your differential equation. Oh, geez. It's t minus 2y. And I'll do the same thing, negative 5 to 5. Uh-oh. Oh, there. Okay. I don't know what that glitch was about. And there's some stuff here. Just ignore these things for now. We'll talk about that, I think, on Monday, what's going on with these settings. For now, you can just click wherever you want. And there you go, right? See how that's pretty close to what I got. I had some sort of like down and back up. Because what Mathematica is doing is it's just saying, here's the slope, and it kind of follows along what those slopes are. Each slope leads to kind of like the next little, you know, in Mathematica's head, it made a slope field with even more lines, so many lines that it just kind of like connected them all together here. So yeah, that's a little bit about slope fields. So let's hit stop share. Oh, and switch to this other camera. Ooh, all right. Get the piece of paper here. See what else I wanted to talk about. Blah, 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 blah. I mentioned that. Hey, I did that. Oh, okay. So we'll talk about that. But maybe let's do this. Oh, yeah, we definitely want to talk about all that. But let's take a 5-minute break. I'm going to push pause, give you all like a screen break here. You know, go do some push-ups or something like that. And then we'll be back. And then I want to talk more about 1-1 and then maybe look at this mixing problem thing. So cool. I'll hit the pause-o button. Okay, this meeting is being recorded. Okay, so let's look back at 1 point. Oh, wait, well, let me open this thing here and this thing. Wait, chat. So, okay, so chat's open. Okay, so let's look back at our simple population model from 1.1 and just kind of remind ourselves of something. Okay, and this is key. dp dt is kp. Now, what I want to introduce, what we looked at, right, this is familiar, right, is we got this and we saw that the solutions to the initial value problems and, you know, whatever, were exponentials, right? That looks something kind of like that, right? Because we solved it and we got, you know, P equals C e to the kt, right? That's our solution to the differential equation, and that's what that looks like. Now, what I want to look at is something called a phase diagram, and this gets pretty abstract. This is familiar, but this is kind of weird. dp, I'm going to do this. dp dt graphed against p. Okay, now notice what this is key because this is going to happen a bunch as the quarter goes along. We're going to look at these phase plots. Now, this is familiar. Population against time, it kind of makes sense. This is rate of change, and you have to be careful what the axes are, versus P, right? And so the graph for this one is going to look something kind of like this. Where the slope is equal to K, right? And that's because it's kind of like y equals mx, right? This is my y, and this is my x, right? So elephants, horizontal slope, bacteria, pretty close to vertical slope, right? So that's kind of the deal with these guys. And it's important because, you know, like, it's just something you probably haven't done is plotting a derivative versus a function. Now, for the population model, you know, algebraically, everything is great here, but is that for a population model doesn't have negative population, right? So there's probably some domain restriction. We would cancel that out for populations. But also, we were kind of talking about that this doesn't make sense because what happens as the population increases? We know that it can't continually exponentially grow forever because of constraints. So what I'm going to do is put a few options up here and just ask you all what you think is most realistic. So I'll put 3. I should draw my axes first. I'm going to fix this. Oh, whoops. Okay, so I put 3 options up here. One of these is more realistic and better approximates what's going to happen. You know, like what we're talking about, I think Aaron mentioned the carrying capacity in the chat. And what I'm going to do is throw you in the breakout rooms for just a second and then have you quickly discuss which one you think is most appropriate. 2 of them are definitely wrong though, right? There is one answer. It's not like, well, in this situation, this might be better or something like that. Cool. So I'm just going to hit pause on the room. Okay. Oh wait, I also want this green pen, purple pen. Okay, so what we have here is a grid here, and let's draw each situation, kind of what's happening here. I want to kind of relate here to here. Let's do this one first, right? So population starts off, right, at P. You know, what you would plug in is, you know, whatever that population is, you know, if this is 10 people, we go to 10 people and find what dP by dt is, right? That gives me a positive slope. And then that positive slope as population increases, right? As population, or maybe let's look here, as population increases, the slope increases, right? And that's what we see here. It's kind of like I'm looking at the y-axis, and as population increases, the slope increases, right? That's like the visual connection between these 2. Now, a lot of folks looked at this. It seems like the rooms that I made, everyone kind of liked this one, but there's a flaw with this one. As the population increases, what does the slope become? The slope becomes a constant.
0?
Oh wait, what was that?
Oh, 0? Like it
Oh
flattens?
yeah. Oh no, not 0. Notice the slope of this graph becomes 0, but as population increases, dP, notice this is tricky, right? Because look at what's in what thing. dP dt becomes constant. And what happens if dp by dt is constant? What kind of graph is that? That's a, what arm is, yeah, linear, right? So as population increases, this one is going to end up looking like this. It'll be like concave up, and then it's going to become a line. So I'll just put concave up, and then it approaches a line. Because notice, as population gets bigger, dp dt becomes a fixed value. Now, I think the confusion is, it doesn't make sense because it's new, the slope of this becomes 0, right? And this becomes a constant. Now, this one is clearly wrong because what happens? This one's like concave up, and then what's going to happen here is it's going to become more and more concave up, right? As population increases, it gets like crazy, crazy steep. So this is like some sort of like crazy exponential going even higher, right? Like something even madly bigger, like e to the 3t or something like that. E to the t to the t. I don't know. We'd have to solve it. Okay, and now this one, what happens? As population increases, the slope increases. The slope becomes a maximum. Let me stand over here. The slope becomes a maximum, and then the slope decreases to 0, right? And so this is the one that's going to look kind of like this. Oh, wait, let me just kind of draw. That doesn't matter, actually. And this is the one that kind of has that fixed population, because notice, as population reaches a certain threshold, the slope goes to 0. So this one is going to be the optimal choice here. Okay, so what I want to do next is maybe attach some numbers to this whole situation here, right? Okay, so how are we going to attach numbers to the thing? I'm going to make a word problem, and I'll do some algebra and stuff here. So the way we modeled, let's go back here. The way we modeled this was we did a line, right? I looked at this and said dp dt equals kp. How can we model this? What does this look like? And you can do whatever, say whatever you want. What's a function that kind of looks like this? Any guesses? Or no wrong answers, really. Let me open the chat again.
Would it be like the sigmoid curve?
Oh, did you say sine?
Or sigmoid, like the S, like the logistic?
Oh, this is called the logistic model. But like, what's an equation that
Oh, that would be a negative squared.
Yeah, negative, a parabola, right? You can kind of see and no wrong answer, right? Anything that has this shape here is going to have this feature in the population model, right? But parabola would work. What else would work? You could do sine and just limit the, some sort of transformation of sine, and that would also work, right? Remember, I kind of said before, a population model. There's no the population model. It's like try different ones and see what works out, and whichever one follows the data the best is probably the best one. But let's stick to, you can probably come up with 1,000 different things that have a little lump right there, but let's stick to the quadratic one. I heard someone say a quadratic. And what I'm going to note is that for the quadratic has a 0 here. So I'm going to just do ax squared plus bx, right? It's not shifted up or down, right? And that makes sense because if population is 0, what should the rate of change of population be? 0. If you have no monkeys, there's no future monkeys, right? So that makes sense. I guess in biology, they used to believe in something called spontaneous biology, where they thought like fungus just grew out of dead things and rats just appeared in garbage magically. That was like, I guess in like, I don't know, the 1400s or something like that. But, you know, it kind of makes sense. You leave garbage out and rats appear. Leave out an orange and mushrooms grow out, or fungus grows on it. Okay, so let's look at this one, and I'm going to just use some variables here. Here's going to be our model, and we're going to solve this differential equation. And we'll do some kind of crazy algebra here. We'll see the algebra that we do. All right, let me kind of look at this for a second. Okay, yeah. So we'll solve this one, and this is going to be our model, right? And let's make some predictions for what's going to happen, right? I did K1P plus K2P squared. K1 is probably positive, right? To reflect that it's kind of at first increasing. And then what's K2 going to be? Concave down, so that for this one has to be negative, right? That's going to be my prediction. And we're going to solve this with some numbers, right? So let's kind of do this. I'm going to say that a rabbit population given no constraints will double every, let's say, 20 weeks. But in Judkins Park, let's just say, the carrying capacity is, let's make it a bunch, 750 rabbits. It's a lot. I don't know if there's actually 750 rabbits in Judkins Park. It is 75. I don't know. We're just making up numbers for this guy. So, okay. And so what we want to do is solve for K1 and K2, given this information about the rabbits here. Okay, so I kind of see two pieces of information that are valuable. One is, given no constraints, the population doubles every 20 weeks, right? So that's one thing. And then we kind of have this other, carrying capacity is 750. Let's deal with this one first and then go to the 750. So what this tells me kind of what I put in air quotes there is this. Is that fair? This is kind of saying the no constraint, right? There's unlimited food, you know, like Judkins Park, Fans Forever, or maybe those first few rabbits that have unlimited access to food have that exponential feel to them. You know, like, oh, right, new place, new clover that I can eat, you know, no predators, everything is great. Under that assumption, we're looking at that linear simple population model, and the solution is an exponential. And I think we can solve for K1 knowing that they double every 2 weeks. Oh, every 20 weeks, sorry, put that on. Every 20 weeks, the population doubles. And the reason is that fair for this guy that C we can even write it like this, we'll see more often. I'm gonna write this as P0, where this is the initial population. Right, and that's because when t equals 0, p is going to equal p naught, right? Plug t equals 0 and you get the initial population. Now, we're trying to solve for K1, right? I kind of just gave a little reminder of some pre-calc stuff. We're solving for K1. I think what I'm going to do is use this double every 20 weeks on the exponential and say 2 P0 equals P0 e to the 20 K1. This is kind of our clutch algebraic move. And notice that's kind of what that's saying is when t is 20 weeks, the population is double the initial population, right? That kind of makes sense. And then the P0s cancel, and we can solve for K1, right? So what we end up with here is we get our trusty TI-83 calculator. And I got, 0.346. Awesome. So we kind of got partway through, right? We're looking for two things. We're looking for K1 and K2. What did we get? We got K1. But what we're missing now is, oh, let me get another pen. Hold on. I want a different color here. Now what we're looking for next is K2, right? The unknown here. I need the pen anyway, so I had to grab it. Okay, so let's do that on this other board. And for this one, you can probably tell this is where we're going to use the carrying capacity. And I'm going to do some algebraic tricks. Well, I'll do the simplest way first and then show you this kind of tricky thing. Okay, so I'm just going to copy our differential equation. All right, K1 is known, and it's K2. Is that for K2 that is unknown here? And let's read through the sentence here. The carrying capacity is 750 rabbits. Now, here's how we're going to solve this. When P is equal to 750, what is dP by dt?
0?
Yeah, that's right, right? And so I think, and we know K1, so is that fair? We have everything here to solve for K2, right? So yeah, we just plug in 0 for dp dt equals K1, which we solved. I'll just put it here now, 3, 4, 6, that's fine, times 750 plus K2, which is unknown, times 750 squared. Oh, divide both sides by 750, right? And then I'll just solve this on my calculator. You can do this on your own, but from here it's just an algebra thing. Subtract. And I got negative 4.8 times 10 to the minus 4, right? And this doesn't like to zoom in when close, but whatever. I'll just do 3 digits. Ooh, no, that's not going to work. Cool. And now we'll call that green. And we got a negative number, which is kind of what that's sort of what we expected, right? Because it has to be concave down here. Cool. So our model is, I'm going to go back over here. I'm definitely going to do one more thing kind of before wrapping this up. Cool. So our in the end, dp by dt is going to be the 0.346p minus 0.000485 p squared, right? And now here's one thing I want to do. I'm going to bring back those k's. Right. Now we didn't solve the differential equation. We just kind of solved for those unknown parameters, right? The unknown parameters, depending on the carrying capacity and the reproductive rate of those rabbits, will determine those parameters, right? But we kind of had to understand what we were given in the problem to solve for K1 and K2, right? That's kind of like the biggest exercise. It's like, P is 750, dp dt is 0, right? It's kind of like the crucial thing for this guy. Now, I want to rewrite this expression a little bit differently, and this is kind of how the book writes it. There's nothing wrong with writing your answer like this. It's great, right? This is accurate. You can solve that differential equation. Maybe we'll do that on Monday. I don't know. But there's a better way of writing it, which is a little bit better, because notice these numbers are kind of weird, right? What is negative 0.000485? You know, this kind of makes sense. It's that like exponential growth rate, K1. But this is just a weird thing. You know, it's this weird number. I'm going to rewrite this, and it'll be a different 2 parameters that we'll see come out of this. So I'm going to factor out a P. I'm going to do something else. Wait, I'm going to factor out a P and a K1. You'll see why. So this is like I only know to do this because I've seen this before. You know, it would take me a while to come up with this on my own. And you will not be expected to do this on your own, you know, on a test or something. blah, blah, blah. Yeah. Okay, now I factored out the K1. Notice that leaves me with a K1 in the denominator here. If I redistribute, I should come back to this guy here, right? It's kind of like what I did was I multiplied numerator and denominator by K1, and then took that K1 out, leaving me with that K1. And now I'm going to do slight rearrangement. I'm going to create this new variable called N. N is negative K1 over K2. And you'll see why I come up with this. It's just a substitution of a different parameter. And if I do that, you can kind of see we end up with this, right? The N is the reciprocal of this, so N is in the denominator, and there's a minus sign, so this becomes a minus sign. And this is called the logistical model. Notice it's an it's a quadratic. Just like this is a quadratic, right? You distribute the P and you get a linear and a quadratic term, but there's just different variables. Instead of K1 and K2, K2 doesn't really have meaning in terms of the rabbits and Judkins Park and the clover and all of that. It's just like a number that makes the concavity work out correctly to get the 0 in the quadratic where we wanted. But if we write it like this, we have our K1, which makes sense. It's our exponential growth rate. We might talk about that on Monday more. And we have N, where N is, notice, when we solved this guy, our 750, right? It's the carrying capacity of the rabbits. Maybe I should have solved this. Maybe I can solve it like this. 750 equals, is that fair? Negative K1 over K2. I guess we were solving for K2 over here, not K1. But from the same thing, we can solve for 750 and see that that's our carrying capacity. And it makes a little more sense, right? It's better when the parameters have context to the problem, right? So you can just plug 750 in here and get your logistical model to work out right? And so that's kind of what's happening with this guy. Okay, let's see if there's anything more. Okay, let's do this. I'm going to go to math. We have just a few minutes. I'm going to go to Mathematica. I'm going to do the DE solver for this. I'll plug it in like this. I'll plug this one in. And what I want to do is just solve a couple initial value problems and see what happens. I'll write them down here. Solve using DE solver on Mathematica. The initial conditions. All of these are going to be just when t equals 0. Neat. Solve using DE solver, right? We'll do the slope field thing and we'll do Mathematica. I don't want to draw, like I said, I'm not drawing slope fields by hand. I hate that. That's dumb. So I'll put these in DE solver and see what happens. So first, let's go to share screen. And let me switch cameras. Ooh, let's do this. Aha. Okay, so DE solver. And the numbers we got were K1 was 0.346 times P times 1 minus P divided by 750. And let's just do T. Might have to do some guessing and checking here. Let's do like, oh wait, how long did it take the population to double? It took 20 weeks. So let's do like 100 weeks. And I'm going to do 0 for the min because it does not make sense to have negative rabbits, zombies. And I'm going to go up to 2000 because P equals 1500 is sort of like was given there. And I'm just going a little over so it's not at the top. Whoa, okay. Now, sometimes this happens with DE Solver. I'm just going to maybe change this to 1,000 weeks and just kind of like mess around until I get some values that look okay. Let's do 500. Well, we can ignore those. We can ignore. Let's ignore those. It's just making the lines really crazy right now. But let's take a look at just our solutions, right? You can kind of, I think you can mess with the slope field settings here and kind of change, you know, like these things, and it will kind of make the lines look a little better. But I want to focus on the solutions, not on, like I think we make these. Oh, there. Actually, I just fixed it. Okay, this one changes the length of those lines. Ooh, okay, now it looks pretty good. Okay, so we learned something, right? The lines are just too long, you know, just the way it's written. Now, a few things. Oh, I'm going to add a D here. P equals 752. I want to do that one. Okay, right. I just added that. B or D as in delta is P, population is 750. But let's do this one first. It says P equals 0. If I plug in P equals 0 here, what happens? Oh, I was a little bit below, but I think a little bit above, but I think it's just my lack of clicking ability. It should be 0 everywhere along here. Maybe I'll just do that one in our heads, right? And this is called a stable solution. A stable solution is when it's a horizontal line, right? And you know it's going to be a horizontal line because then I plug P equals 0 into either equation, the slope is 0 and it should be 0 forever. So it'll just be a horizontal line. And it's only doing a non-horizontal line because I'm like clicking 0.1 rabbit and it kind of like ends up multiplying, right? So if I was better at zooming in here, it would just stay horizontal forever. All right, 300 rabbits. So we go over here to 300, and what we see, kind of like what we predicted, population increases and then stabilizes right there at 750. What happens when we have 1,500 rabbits? Too many rabbits, not enough clover, the population decreases and then stabilizes at 750. And then what happens when we click 750? I'm pretty close to it. This is another stable solution, right? Stable solution, like I said, if the slope is 0, it's going to be 0 kind of forever here. So kind of the last thing, I'll kind of bail out of here. Let's go to this part of this board. So stable solutions are when the derivative are zero and they're always horizontal on the P versus T graph. Now, one last thing, vertical are not stable solutions. You can have solutions to differential equations that are vertical. We'll see some examples of that. But notice if it's not really a stable solution if it's vertical, maybe there's something that's like tangent and it becomes vertical right here. Notice this is not stable because if anything, this is like the most unstable because the population is going to infinity in a finite amount of time, right? So keep that in mind. Vertical solutions are not stable. It's only horizontal ones. And, you know, for some other, obviously it doesn't make sense for a rabbit population, you know, to have vertical because then it's like infinite over such a short time. But for other things, something, you know, there are differential equations where it might go to infinity, right? That's a solution. Or it might just have a vertical line in the solution right here, right? Somehow that's part of the solution set. That's certainly possible. Ow. Okay, well, it was good to see you all today, and I think that kind of covers it. What we'll do on no class tomorrow, right? What we'll do on Monday is look at Euler's method, and then Tuesday we'll look at our first project, right? So I'll probably post it on Monday, but we'll talk about it on Tuesday. So I will see you all then. Have a great weekend or whatever, and yeah, and or on the Panopto, right? Maybe you're watching this on the Panopto. It's another time. All right, peace out.